Good morning, Knights. So today we're going to be talking about electron configuration. So electrons, we all know what they are. They're the negatively charged part of the atom, and configuration basically tells you where they are. So if we were to talk about a room's configuration, we're basically talking about where the desks are, where the stuff is. So configuration is basically where things are. Electron configuration, that tells us where electrons are. All right, so I'm not going to read all of this. Just want to tell you today we're going to be talking about quantum mechanics. And quantum mechanics tells us where very tiny things are. Heisenberg, you've probably heard of him if you've seen the show Breaking Bad. Most of you probably haven't. But Heisenberg, he was the person who figured out that if you know where something is, then it's impossible to know how fast it's moving. And if you know how fast it's moving, it's impossible to know where it is. Using his principle, we're able to say, not definitively, but we are able to say where things are. Let me move my picture real quick. All right, so when we talk about quantum mechanics, there are 1 to 7 levels. We'll talk about them in a minute. You don't have to write any of this down. I'll tell you when you need to start writing. So you don't need to write this down, but I do want to tell you about it. So the sublevels we're going to be talking about today, that's the most important part of this page. The sublevels we're going to talk about today are called S, P, D, and F. So the S block, which we'll talk about in a minute, it stands for sharp. You don't need to know that. P stands for principal, D stands for diffuse, and F stands for fundamental. So none of this matters to you. I'm just going to go ahead and move on to the next slide. So here's where it does matter. So everybody grab your periodic table. It would be very helpful if you wrote some of this stuff down. So we're going to break the periodic table into blocks. So this first block right here, So this first block right here, we're going to call the S block. So this is the S block. And the S block can hold 2 electrons. This is electron number 1. This is electron number 2. That's the S block. Next important one you need to know is the P block. So this is our P block. The P block, as you can see, can hold 1, 2, 3, 4, 5, and 6. Next one you also need to know is going to be the D block. This is the D block. The D block holds 10. So the D block, it holds 10. That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then the last one, this is the one that we hardly work with, but you do need to know what it's called. This one is our F block. And the F block holds, let's count them. So here we got 5, 10, 15. I didn't realize it was 15. I thought it was 14. But it holds 15 total electrons. So these are the blocks. You need to know where each one is. So S block, very important. We're going to work with this one a lot. These two are the S block. This over here is our P block. Down here we have our D block, and then here we have the F. So I know nothing makes sense yet. It'll make more sense as we continue moving forward. All right, so inside these sublevels are orbitals. So you know what an orbital is. So here's the sun, and then here's Mercury. That's Mercury's orbital. Venus's orbital, Earth's orbital, and then Mars's orbital. And basically what an orbital is, it's the path that something takes when it's revolving around something else. So in the case of electrons revolve around the nucleus, and they revolve in an orbital. That's basically what an orbital is. So we were talking about Heisenberg's principle. When we mention an orbital, we don't know where exactly the electron is on the orbital. We just kind of know a path that it's going to take. And that's basically what orbitals are. It's 90% probability we could tell you that it's within that orbital, the electron, which is close enough for us because we do need to know where they are. Now back to these guys right here. So the S block, and this is sort of important. I would write this down. So the s block orbitals, you don't have to write it all down. All you need to write is the s orbitals are spherical. So it says spherically shaped, so spherical is enough. So you can get rid of the ly and don't worry about any of this. And of course they revolve around the nucleus because they're revolving around their protons. And then we have the p orbitals. The p orbitals are barbell shaped. So don't worry about the rest of it, just the p orbitals are barbell shaped. So what's a barbell? A barbell is basically a figure eight. So it's the things you use to lift weights, that's a barbell, and it looks like a figure eight. So if this was our proton and neutron, the electrons are going like this. And in the p block, you actually have more than one orbital. So in the s block, you only have a single orbital. So let me draw them for you. So here's our nucleus, and our s block is going to be just a circle that revolves around it. And each orbital can hold 2 electrons, and basically there's a possibility that there are 2 electrons in here. So let's say this is helium, there are 2 electrons in here. Now let's say it's lithium. If it's lithium, then it's got this s block, and it's also got this barbell shape, and then this is holding 2 more electrons, or 1 more electron, because lithium only has 3 total. And that electron could be anywhere in that barbell shape. And as you move forward, as you gain protons, you're also gaining electrons, and you're also gaining orbitals. So here's another figure eight, and this figure eight, it also holds 2 electrons, and we're going to talk way more about these in a minute. So next we have our D and F block. We don't really need to know the shapes of these. Just know that they're very complex. I'm about to show them to you. But the ones that are important to know is the S block is spherical, and it's the first layer. So here's our nucleus. This circle that goes around the nucleus, that's our S block. And we could have larger S blocks, and we will. We'll talk about them later. But they're just circles that revolve around the nucleus. And then the P blocks, these are the figure eights. And there's going to be multiple levels of them too. So we have a figure eight that's this small, that's going to be a lower level than this one that's much larger. All right, so each sublevel has room for different amounts of electrons. The S sublevel can hold 2 electrons, so it has 1 orbital. The P sublevel can hold 6 electrons. So this is very important. Where we wrote about their shape earlier, this is the next thing you need to write. So the S sublevel can hold 2 electrons. And if you want, you can include that it has 1 orbital. But the important thing to know is the S block can only hold 2 electrons. And if you look back at that periodic table, you saw that the first 2 levels, and I labeled them for you, 1 and 2. So that's going to be our S block, and the S block can only hold 2 electrons. Here's our D block. We said that it holds 10, and then our P block, which holds 6. And then our F block, which goes down here, holds 15. I guess here it says 14. It is 14. It's not 15. I said I was confused earlier, but no, it's definitely 14. It's just that periodic table looks a little bit different. So here we have 2, 10, 6, and 14. But yes, this is what you need to know. So actually, I would go ahead and write all of this down. So P sublevel can hold 6 electrons. This is very important to know. And it's easy to remember because we have 1, 2, 3, 4, 5, and 6 places for elements to go in the P block. In the S block, we only got 2 places for them to go. They can either be the first element in the S block or the second element, which tells you that you have 1 and 2 electrons. And then finally, the D sublevel can hold 10 electrons, so it has 5 orbitals, because each orbital holds 2 electrons. So the F sublevel can hold 14, meaning it has 7 orbitals. We're going to spend very little time talking about the F block. It's the least important for us here in high school. So I'm going to pause for a second. All right, so let's go ahead and move on. So yeah, the F block can hold 14 electrons, meaning it has 7 orbitals. Let's go ahead and move forward. All right, so here's our S level, and we just talked about these earlier. So our nucleus is right at the center, and then the orbital, it's a sphere that surrounds the nucleus. And then here's our P level. So our P sublevel, it looks like a barbell, and we already said that it holds 6 electrons. That's because it's got a total of 6 orbitals. So here's our first one. This is 1 electron, 2 electrons, and then here's our second one, which looks exactly the same except it's a different angle. So here's our 3, and then here's our 4, and then finally this one, that's our 5 and our 6. You put them all together and it sort of looks like a sphere as well, but it's going to be a total of 6 orbitals that hold 6 electrons, and this is a level that's above the first S block. And we're going to talk more about the layers, but earlier when I mentioned that there were 1 to 7 layers, this is what we were talking about. You don't need to write this. This is just pictures so that you understand what I'm talking about. You don't need to write anything here. All right, so next we have our D sublevel, and then here's the D sublevel. It's a very complex one, and I'm just showing it to you. You don't really need to know what this one looks like, just showing it to you. And as you can see, when you put all these sublevels together, it sort of looks spherical. It's not spherical, but it sort of looks like it is. And then finally, here's our F block, the most complex of all of them, and also at the end sort of looks like a sphere, but it's not. Just so you know what they look like, let's go ahead and move forward. All right, so to know the maximum amount of electrons that could be at any principal quantum level, the elements could be represented by the formula 2n2 if n is 1. Don't worry about this. All right, so here's where things get kind of cool, kind of confusing. So we're going to talk off Aufbau's principle. So Aufbau's principle tells us that electrons fill lower energy levels first, thus 1 before 2 and S before P. So basically, think about it like you walk into a teacher's class on the first day of school and he says, okay, go ahead and fill the front row, and you can't sit in the row behind it until you fill the front row. Or when you were in junior high and you were in the cafeteria and they said everybody had to sit in order and you just had to take the next seat. You couldn't just pick your seat. That's basically what electrons do. They can't pick where they sit. They're just going to sit in the next available seat. So that's Aufbau's principle. And orbitals in the sublevel are equal energy. So if you're in the 2p, everything in the 2p has the same amount of energy. This isn't really important to you guys, but I'm just explaining to you parts of Aufbau's principle. What you need to know about Aufbau's principle and what you should write down is what I put over here in brackets. So electrons will fill lower energy levels first, thus 1 before 2. All right, so next, the principal energy levels often overlap. Don't worry about that one. And then next, we have boxes are used to represent orbitals. So I'm about to show you what that means and how boxes represent orbitals. All right, so this diagram is very important for the assignment you're going to be working on today. I would take a picture of it right now, or I would draw it. Drawing it is not a bad idea. I would definitely draw this in your notebook. So pause here for a minute. And this thing, I know it looks more complicated than it actually is. Here's how you're going to do it. So you're going to go 1s. So 1s is by itself. Next, you have 2s. So I'm just going to put the s's all the way down. So then you got 3s, 4s, 5s, 6s, and then 7s. These represent the 7 levels that we have. And then 2p starts at the 2s. So 2p, 3p, 4p, 5p, 6p, and then 7p. And then 3d, it starts at the 3p. So right here at the third energy level, we can start out our d's. So we got 3d. And just to show you a little bit more of what that actually means. So I'm gonna draw a fake periodic table again. So here's our S block, here's our D block, and then here's our P block. And as you can see, the D block, where does it begin? It begins at period 3. So period 3 is where the D block starts. So here we have period 1, period 2, and then at period 3, the D block starts. So 3D, 4D, 5D, 6D, and 7, and then we'll talk about those in a minute. But then we have 4F. 4F starts at the 4th energy level, and then 5F. So this is Aufbau's chart. You're going to use Aufbau's chart. Let me move my picture out of the way, just so I'll get a good image of it. But with Aufbau's chart, it basically tells you where electrons are going to go. It's sort of, I don't know, the seating chart. So the way it's going to go is you're going to put an arrow going through the first one, meaning the first orbital, the 1s, is going to be the first one that you fill. Your next arrow is going to go through 2s. So after you fill 1s, you fill 2s. After you fill 2s, you're going to fill 2p, and then after 2p, you fill 3s. And it's going to get a little bit confusing in a second. So after you fill 3s, you're going to fill 3p, and after 3p, it's 4s. And it gets confusing because you go from 4s to 3d. So 3d, then 4p, then 5s. And then from 5s, you're going to go to 4d, and then 5p, and then 6s. And then from 6s, you're going to go to 4f, 5d, 6p, and then 7s. And I know this makes no sense right now, but it will very soon. Very good idea to take a picture of this thing now that I've, cleared the page for you. And if you're ever looking for it, just look up Aufbau's chart. You'll find it in Google Images. All right, so Pauli's exclusion principle, you don't need to know about this. Don't worry about anything here. All right, so Hahn's rule. Hahn's rule matters. You don't need to know what it's called. I'm just going to tell you what the rule is. The rule basically says that you can't, so earlier when I was talking about we represent it using boxes, just imagine these as boxes. So this is a box, this is a box, and this is a box. And each box basically represents an orbital. And we already said that orbitals can hold 2 electrons, which means you need to put 2 electrons in each box. And the way that you're going to line them up in these boxes is going to be, so you're always going to go, so let me just draw the boxes for you guys. So basically you're going to go 1, 2, 3, and then 4, 5, 6. It has to look like this. If you draw it any other way, it's wrong. And basically what that means is, it's what you see here. So you're not able to fill this one first. So you can't go like this, and then in the next box you do this, and then the next box you leave that empty. You can't do that. You have to fill all 3 boxes. You have to just go in order, the same way we did the electron, the Lewis dot structures. So be sure that you're filling all the boxes before you come back and fill the original box. And we're going to do some examples of this. All right, so here's the boxes that I was talking about before. And let me hit the next one. All right, so I'm going to label these. So this is our 1s, 2s, 3s, 4s, 5s, and 6s. So this doesn't have all of them. It's just got a few. And then after that, we got our 2s, this is 2p, 2p, 3p, and then here's our 4p right here. And 5p, but you don't really need to know what these are called. All you need to know is how electrons fill them. So if you were dealing with if you were dealing with hydrogen, then hydrogen has 1 electron. That 1 electron is going to fill the first box first. So we were talking about placement. They're going to fill the bottom first. This is where they're going to go. So they're going to start right there. And hydrogen has 1 electron, so that 1 electron is just going to be an up arrow. Next element we have is helium. So helium has 2 electrons, therefore it has 2 arrows. So the second arrow is going to fill the first box. Next we have lithium. So I'm just going to show y'all a bunch of different elements, and then later on we're going to write them down. So lithium has 3 electrons, so the third electron is going to fill the second s block, the second s orbital. Then there's beryllium, so it fills the same one, just puts that 4th electron there. And then boron, which is right at the p block, is going to be the first one to fill the p orbital. So I'm going to show y'all what these look like when we write them down. So I'm going to go back to hydrogen. So hydrogen, when you want to write out its electron configuration, because this is just an illustration of it, when you want to write it out, it's going to be 1s1. So this one tells you which level you're talking about. This tells you which block you're talking about. And then your exponent tells you how many electrons fill that block. So 1s1 means you have 1 electron in the s block, in the first S block. Next we have helium. Helium is going to be 1s2 because we're in the 1s block and we have 2 electrons in that block. Then we have lithium. So with lithium, first we have to fill the first block. So we got 1s2 and then 2s1. So basically 2 electrons in the first box, 1 electron in the second box. Beryllium is going to be 1s2 and then 2s2. And we're going to do a lot of these, so, you know, get used to it. And and you're going to be going back and forth. So they're going to give you the element, ask you for the electron configuration. They're also going to give you the electron configuration, ask you for the element. And the easiest way of finding out which element you're dealing with is you're just going to count up the electrons, because these exponents are telling you how many electrons you have. So when you have 4 electrons, which element are you dealing with? You're dealing with beryllium. All right, so next we have boron, and then here you can see that we just filled our first P block. So this is going to be 1s2, 2s2, and then 2p1. And then carbon is going to be 1s2, 2s2, and then 2p2. So all you got to do is count up the electrons. Here we have 6 electrons. 6 electrons means 6 protons. 6 protons means carbon. All right, nitrogen, as you can see. So we're just going to keep moving forward. I'm going to go forward a little bit more. I actually have a lot of these, but let's go ahead and write this one out. It's important to see that we fill all of these first. So we go up arrow, up arrow, up arrow, and then we come back with our down arrow. So keep that in mind. So let's go ahead and write this one out. This one is going to be 1s2, 2s2, 2p6, and then 3s2, and then 3p4. So then we're going to count up our electrons. So the first 3, so 1s2, 2s2, and then 2p6, these equal 10. And 10 plus 2, so we're 12. 12 plus 4, that's 16. So 16 electrons means 16 protons. 16 protons means sulfur. All right, so next one, basically the same thing. Here we have our first D block. So this is going to be 1s2, 2s2, 2p6, and then 3s2, and then 3p6, and then 4s2, and then we're going to go down. So 3d10, and then 4, and then it's just 4p2. So to find out which element it is, you're basically just going to count them up. So as you can see, as you move forward, all you're doing is you're increasing the length of this thing. So every element on the periodic table has every block and orbital as the element before it plus 1 more, because as you move forward you're adding a single proton. Adding a single proton means you're adding a single electron, which means every time you move forward 1 step on the periodic table, you have everything the previous one had plus 1 more electron. And this is why Aufbau's principle is important. That chart that you drew with the lines, you're going to use that to tell you where you're going to put the next electron. And it's only important when you're going in that direction. So I can write this for you, but there's really no point. I'm just going to stop right there with drawing these out for you. So here we have a neon atom. A neon atom has 10 protons, 10 electrons. Here's our 10 electrons. So 1s2, 2s2, and then 2p6. And this is basically what it looks like. Not really important, just wanted to include it. All right, don't worry about that. All right, so here, let me pull up Aufbau's principle just to show y'all how we're going to solve stuff like this. Because even like, you know, this thing takes, it's easier to have the chart in front of you as you work through these, just because I don't want to, you know, go off the top of my head and show y'all something that's incorrect. So I'm looking at Aufbau's principle on my second screen, and I'm going to fill this out real quick. I could just show you the next page, which has the answer, but I want to show y'all how to solve these. So nickel has 28 electrons. If we want to see the electron configuration for nickel, we're just going to start filling our boxes. So first box we're going to fill is going to be 1s2. That's 2 of our electrons. Next we have our 2s2. And then we have 2p6. And basically I'm just counting electrons up until I get to 26. So after 2p6 we have 3s2. After 3s2 we have 3p6. And then after 3p6 we have 4s2. And this is a trick that I use. The first 3 always equal 10. The next 3 always equal 10. So we're at 20 so far. And after 4s2 we have 3d. And that's going to be 3d. And how many electrons do we have left? We have 8. And we know that d holds 10. So this is going to be 3d8. And let me show you another cool thing about the periodic table. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. 3d10 is the one that matters the most. That's telling us exactly where the element is on the periodic table. Let's look at the periodic table. So 3d10 is going to be right here. Oh, shouldn't have done that. All right, so 3d10. So I know this is the 4th level. Okay, it's not letting me draw anymore. But here's 3d8. So this is going to be our d1. So that's d1, 2, 3, 4, 5, 6, 7, and then 8. So 3d8. Let's get the next one. So this one is 50 electrons. So we're just going to do the exact same thing that we did before. And we're just going to count up our electrons up until we get to 50. So, and I know this gets kind of boring, but we do need to learn it. You will be tested on this. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And let's count these up. So first 3 always equal 10, next 3 always equal 10, and then the third one by itself equals 10. So we're at 30 so far. And then 4p6, and then 5s2, and then 4d10. So here we're at 8, and then 18. So 18 plus 30 equals 48. So at this point, we're at 48 electrons. We only need 2 more. And then after 4d, we have 5p. So 5p2. Now let's take a look at our periodic table, and let's see where 5p2 puts us. So 5p2 so here's 5, 1, 2, 3, 4, 5, and then we're going to go to our P block, 5P1, 5P2. 5P2 is SN, which is tin, and let's see if that's what we were looking for. We were looking for SN, which is tin. So our electron configuration also tells us exactly where things are on the periodic table. And I know y'all think that's useless, but no, it's actually, there is a purpose to it. So let's go ahead and move on. All right, so next thing I want to show you guys is shorthand configuration. So shorthand configuration basically tells us how to draw something without how to write out the electron configuration for something without writing the entire thing. So as you saw before, every single one has everything the previous one had. So one way we could shorten all the steps so that we don't have to do this 100 times is basically we write out neon. So let's say Ne. So we're going to write out neon, and we're going to put that in brackets, and then we're going to write out the configuration that comes after it. So after neon, we're going to write 3s1. I'm out of space, but that basically tells you everything you need to know. So neon and then 3s1, which basically means we're dealing with sodium here, and that's. So what you're doing is when you put in neon, that means you're including all the electron configuration for neon, and then when you write out 3s1, that means so neon plus 3s1, which puts you exactly right here at sodium, which is where you want to be anyway. So you're going to get some practice with shorthand configuration. It's not as hard as it looks. And the important thing to know about shorthand configuration is you're always going to use a noble gas. And then anything you're going to write after, it's just going to be after the noble gas. So let's say you're writing let's say you're looking for silver, which is 48. So the shorthand configuration for silver is going to be krypton. So Kr, should be capital K. So Kr for krypton, and then you're going to include the S block, which is right here, and then you're going to include the D block all the way to here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So just to write that out, that's going to be 5s2. So krypton, and then 5s2. And then after 5s2, we got, so this is 3d, this is 4d, so 4d9. And then after 4d9, we have 4d10, and then after 4d10, we move on to the next p block. All right, so let's go ahead and move forward. So that's basically what shorthand configuration is. Instead of writing everything for polonium, you're basically going to write xenon, which is the noble gas, and then you're going to write everything that comes after xenon, which is the 6s plus all that stuff. So it does shorten things considerably for you, especially if you're doing a lot of electron configuration. All right, next I just want to review Lewis structures. I know y'all remember them. We did them last class. So there's not much to it, but I do want to go over it real quick. So here's lithium. Lithium is going to be 1s2, 2s1. So to figure out what it is, all you're going to do is count up your electrons. So 2 plus 1, 3 electrons. 3 electrons means 3 protons, which means you're dealing with lithium. Beryllium, 1s1, 2s2, 1s2, 2s2. And basically you're just counting up your electrons, 4 electrons, and that means you have 4 that means 4 protons, which means it's beryllium. So this only works for full configuration. It's if you were doing it for shorthand configuration, you would count up all your electrons, and then you would add the number of electrons that the noble gas has. So if it's neon, that's right here in the beginning, then neon has 10 electrons, and you're just going to add that to the number of electrons that you counted up. But anyway, beryllium, here's your electron configuration for beryllium. Just wanted to show y'all what those look like. So next we got boron. So 1s2, 2s2, and then 2p1. And then, as you can see, 3 electrons for boron. Carbon. I just included a bunch of them just to show you guys what these things look like in electron configuration and Lewis structure. So these things, they actually go hand in hand. So nitrogen, oxygen, fluorine, neon, strontium, bromine, And that's it. That's basically the whole thing. I'm gonna go ahead and end it right there.